네, 안녕하세요. 바이오 인스파이어드 아티피셜 아이스를 주제로 설명할 한혜성이라고 합니다. 네, 논문의 순서는 다음과 같습니다. 인트로덕션, 그리고 아이 이볼루션과 하이 레졸루션 비전에 관하여 소개하고 바이오 미미크리 of single chambered ice, 바이오 인스파이어드 컴파운드 아이스, 그리고 바이오 인스파이어드 비주얼 프로세스에 관하여 소개합니다. 그리고 결론으로 마무리 짓는데요. 저는 1번과 2번을 중점적으로 설명하겠습니다. 바이오 미미크리 of single chambered ice를 주제로 설명을 하도록 하겠습니다. 발표에는 영어를 사용하도록 하겠습니다. 인트로덕션입니다. Humanity has devoted significant effort over a long time to the development of imaging devices capable of detecting and recording moving objects as humans see them. Camera-related technologies have matured continuously, imitating key factors of the human eye, such as the lens and retina, using artificial optical lenses and electronic devices. The current level of digital camera technology has reached and surpassed the capabilities of biological eyes in terms of resolution and perception mechanisms. However, regarding simplicity, miniaturization, energy efficiency, and certain functional aspects, conventional imaging technologies still have significant room for improvement compared to animals' eyes. For instance, common digital cameras require complicated lens configurations due to the mismatch between the imaging surface and the focal plane, whereas the natural eyeball only has a single lens. Efficient light management in the natural eye, such as light accommodation or adaptation, is also an important natural facet that should be mimicked in artificial eye research. In contrast to the human eye, that is a single-chambered eye, compound eyes as it can be found in insects, crustaceans, and other arthropods are particularly remarkable for their extremely wide field of view, nearly infinite depth of field, and high motion of sensitivity. The potential application of compound eye-inspired technology include navigation and sensing devices, biomedical endoscopies, and security cameras. Another important stream of bio-inspired image sensory research is medical application, such as the visual prosthesis. Human eye-inspired optoelectronic systems can restore the vision of patients with retinal degeneration. Recently developed flexible and stretchable electronic technologies combined with soft materials and devices have facilitated the development of a new class of imaging systems and visual prosthesis. Eye evolution and high-resolution vision. The evolution of the eye was driven by the demand for the capability to process more complex sensory tasks. As the amount of information increases, the necessity information processing capability gradually becomes more complex, thereby necessitating more sophisticated sensory organs shown in Figure A. More complicated tasks, such as the detection of prey or predators, visual communication, and mate recognition, have led to high-resolution vision. Thereby, evolution to the most efficiency sensory organs matching with the inhabited environment has yielded these four classes of eyes. High-resolution eyes, such as the human eye, shown in Figure B, and opposition compound eyes, shown in Figure C, are representative of single-chambered eyes and compound eyes, which are typically found in vertebrates, chelicerates, and insects, crustaceans, respectively, have triggered a recent renaissance in bio-inspired imaging systems. The remarkable imaging features of the human eye originate from the unusual refractive index distribution that reduces aberration in the crystalline lens, a focal length tenability by a crystalline lens and ciliary body, and the hemispherical retina that facilitate a wide field of view and low aberration. A sophisticatedly formed position compound eye can simultaneously capture several objects in a wide field of view without a human movement due to its hemispherical shape and the individual imaging of each ametadium, which is a single image unit. Individual imaging, which is enabled by micro-optics and Rabdom, offers at least three advantages: a nearly infinite depth of field, high motion sensitivity, and the absence of geometrical distortion and aberration. Biomimicry of single-chambered eyes. In natural, in nature, many animals, including both vertebrates and invertebrates, such as octopuses, squids, and spiders, have single-chambered eyes. Depending on their habitat, lens shapes are classified as either spherical or aspherical because the lens's desired focusing power differs. Animals' position in the food chain also affects the feature of their eyes. For instance, the eyes of predators are placed frontally to provide wide binocular fields and have a phobia capturing objects at high resolution. The two images captured by the eyes present slightly different perspectives and hence offer depth information. In contrast, animals considered as prey possesses laterally directed eyes and very little binocular overlap. Although single-chambered eyes have a broad distinction according to habitat and food chain, a single lenses and hemispherical retina are commonalities in all single-chambered eyes. Therefore, implementing a high-performance single lenses and hemispherical retina are key points in the biomimicry of single-chambered eyes. Artificial optical apparatus mimicking biological eyes. Human eyes possesses an aspherical crystalline lens with a graded refractive index lens screen distribution to correct optical aberration, shown in Figure A. Unfortunately, materials with GRIN green capabilities are scarce among glasses and polymers that can be exploited as optical lenses. Therefore, modern optics employ the option of using multiple lenses with different optical dispersion to compensate for aberration, but this typically demands heavy and large optical design. Hence, the, the fabrication technology of aspherical green lenses can offer many advantages to modern optics, including simplicity of optical systems and low incidence of optical aberrations. The spherical green lens that can be found in many aqueous animals exhibit more appealing optical features due to its shape compared to lens creatures, including the elimination of most aberration and the capability to capture panoramic views. In human eyes accommodation, which refers to adjusting the focal length by changing the shape of the crystalline lens with the support of the ciliary body that acts as a contractor muscle, is vital for obtaining a clear image of objects at different distance, is clearly shown in Figure D. Excessively strong light can damage the retina and weak light hinders object recognition. The human eye has an iris to adapt to light environment variation. Its adaptation is shown in Figure G. Retina-inspired curved photodetector arrays. The arc-shaped of the retina is most single-chambered eyes offers inspiration for reducing optical systems complexity. As with the correction of optical aberration, flattening the optimum focal plane of an optical design requires a multi-lens configuration, which is complex, large, and heavy. Meanwhile, the use of a curved image sensor facilitates a simple optical configuration by matching the image sensor with the focal plane. Curving thinly ground CMOS CCD image sensors serves as a strategy for mimicking the retina's curvilinear shape. Thin silicone near 25 micrometer can provide low strain for a curved imager and hence can be curved to a radius of less than a millimeter without fracturing. In this scheme, the curved image sensor based on a Berg CMOS CCD image sensor is formed by thinning, placing the thinly ground image sensor into a mold and deforming via pneumonic pressure, shown in Figure A. And the Figure B highlights a successful example with a near 19 millimeter radius of curvature, which is the highest curvature attained in a curved image sensor to date based on this scheme. Other strategies use intrinsically soft materials or additional optical systems to capture images on a curved focal plane, for example, organic material or zero-dimensional, one-dimensional, two-dimensional nanomaterials and perovskites. Inherently soft materials provide high bendability and thus facilitate the fabrication of highly curved photodetector arrays, is clearly shown in Figure C. And lastly, retina-inspired curved photodetector arrays. However, hemispherical deformation of planar photodetector arrays with flexibility is difficult because additional stretchability is required in 3D deformation. One approach to enhancing the mechanics is the development of concavely curved photodetector arrays with a strain releasing isolation design, shown in Figure D. A thin silicon layer on a silicon-on insulator wafer form second-dimensional silicon photodetector arrays, and polyamide films encapsulate the prepared photodetector arrays, and mesh structure method interconnectors are used for mechanical stability and a passive matrix layout. Transferring the complete device into an elastomeric substrate means that the overall layer, including the photodetector array, obtain a softness that facilitates 3D deformation. A Kirigami-based device design scheme introduces softness to a photodetector array. In this scheme, a photodetector array with an elaborate petal pattern is fabricated, shown in left side of the Figure G, and then transferred to a concave hemispherical holder, shown in right side of the Figure G. Recently, Wu and others reported a hemispherical silicon-based photodetector array by applying the Kirigami method, is clearly shown in Figure H. Silicon of thickness less than 20 micrometer supplies materials flexibility, and the tessellated hexagonal structure enable structural flexibility, both of which help form a hemispherical imager. Therefore, Highly deformable photodetector arrays can be fabricated by introducing a kirigami-based design. An appealing feature of this scheme is that it yields high pixel density, which is difficult to realize with a mesh structure strategy. It's clearly shown in Figure I. It's all about my presentation, and thank you for hearing.